And you see, when you look at a manuscript, essentially, a lot of the conversation around this is you see your frequency tables, you see figures, they report measures of central tendency. Sometimes they are reporting the mean. If that data is normally distributed, they are reporting the median, and they are reporting some kinds of measure of dispersion around those. We're not talking about those measures of dispersion now. We will talk about them as we move forward. After you've seen that, the next thing you see in your paper is you see some tables. A lot of times they are frequency tables, relative frequency tables. We've learned how to read those. The next thing that you see in your manuscript is a number of graphs. And graphical display, in a sense, is an art. The more you do it, the more you tend to intuitively be able to figure out what's the best display for my study, or whether this, how do I interpret the graphs that people have in this study. But there are certain basic principles that we can pay attention to. The first thing is that the graph should actually tell the story that you want to tell. The essence of a graph is to tell the story of your data in a way that's captivating and that's accurate, and being a very good summary for it. But I tell you, there are so many graphs out there where the caption says something else, the axis say, the caption tell you something, the axis tell you something else. So I'm going to show you a number of, we're going to go through a number of graphs right now, and we'll see. So the first kind of graph that I'd like to talk about is the histogram. We'll be talking about the histogram all the while, so I know you're kind of familiar with this. Usually, here, what you have in the histogram is that in the y-axis, you have the frequency, and in the x-axis, you have the values. So here, for instance, in the first one here, now the histogram usually is used for continuous data. Therefore, you don't see unique bars. No, what you see is a set of bars, that are a set of bars that are adjoining each other. And what's happened here is that the continuous data has been broken down into bins. So, for instance, maybe all the observations we have in this data set is between 1 to 50, and now we've broken it into those from 1 to 10, 11 to 20, 21 to 30. And now we're looking at how many observations actually fall within each of these bins, each of these categories. And we're plotting that on the graph. And that's how you get this histogram graph. The bar chart, most often, the bar chart is just like the histogram, but most often, the data we're talking about here is it's categorical data. And of course, when you're dealing with nominal data, the bar chart is often the only option that you have. Let's move on. Next slide. So I just spoke about continuous data being broken into bins for histograms. Now, there's a lot of art to figuring out what is the bin size that makes sense. Because if the bin size is too small, it might be difficult to have a compact graph. But when the bin size is too large, is too big, you might also obscure some important characteristics of your data set. So for instance, look at these two graphs we have here. This is essentially showing the same data set. The only difference here is that the bin size is different for each of them. Now, when you look at the one to the right, because the bin size here is smaller, you can see that. So for instance, if you look at the one to the left, if you want to interpret this, you would say that, well, there's about 14,000 people who are making between 0 and 100 calls. Well, that's true. But what you don't learn from the graph from the left, is that about 7.6% of this whole data set actually do not make any calls at all. It's actually just 0. And that seems like, if you're looking for a single figure, if you look for the mode in this whole data distribution, what happens, I mean, 0 is actually the mode for this data distribution. That might be very important information depending on what decision you are hoping to take based on your data analysis. So essentially, what is an appropriate bin size depends on what kind of question you're trying to answer, what kind of inferences are you trying to draw from your data set. And usually figuring out what bin size is appropriate for a histogram based on what kind of question, what kind of inferences you're looking for is on art. It's something that you get to develop over time. You get to understand much better over time by practicing, by developing histograms for different kinds of purposes. Let's move on. So, I mean, the bar chart, I mean, we mentioned the bar chart earlier. These are common examples, common ways in which bar charts are used to illustrate comparisons. Sometimes people do stacked bar charts, you see. So for instance, you're looking at a data set where there are 2 categories, maybe there are males and females, and you want people to see from the bar chart what is the relative frequency between males and females. You can have a stacked bar chart where you have females, you have males, you color code it, and somebody just by barely looking at this bar chart, somebody can tell that, oh, there are more males in this data set than there are females. And you know, most of the females, I mean, when you go beyond age 50, you almost just don't find any female at all. Those are inferences that people can easily draw from this bar chart, just based on the fact that you have a stacked bar chart and you have color codes. Another way in which you could have that data could have been presented is to just have side-by-side comparisons. For each of the figures, you have the 2 categories. I mean, you have bars for each of the 2 categories, and those are color-coded. Both are valid ways of presenting this data, and they can be very informative. I mean, just whatever you feel comfortable with is what you can make a choice of whatever you feel comfortable with. Both are very valid ways of presenting discrete data. Next slide. Now let's look at a couple of graphs. How much more time do we actually have?
We've actually run out of time, but I just imagine we're going to go through the slides very quickly.
So, I mean, look at this graph, for instance. Please. One of the big problems here is that, number one, aesthetically, this is the default graph to work with. But just substantively, you can see bars that are overlapping a number of categories. How do you interpret that? So, and the differential sizes in the size of the bars actually add very little information here. Now, this is another graph. This suffers from the same kind of problem. The differential sizes add very little information. Number 2, what is the purpose of these particular, shapes that are being used? A bar would have been simple enough and just communicate the same information. And then you can, if we just don't have enough time, if I ask people to try to interpret some of these graphs now, you can tell that there's going to be a lot of confusion about whether a half person or the feet only that you see on this on the graph on the right. How do you interpret that? So essentially, your graph should be as simple as possible. Otherwise, there's no point introducing all sorts of complications in the graph interpretation. Next slide. Now, this is another one. The problem here with this slide, and that's why simplicity is the first, is the most important rule in any of this, in graphical displays. So, all these slanting axes, the slanting graphs, the only thing they add to these graphs is confusion. The second thing is that when you use color codes, when you use colors, unless you're communicating something with the colors, in which case you need to have a legend. Unless you're communicating something with the colors, there's no need to create a rainbow in your bar chart. Now let's move on. And if you have to use, if you have to use color codes, ensure that there's a legend that is accurate and that is clear. I think we should move to the next slide.
Okay.
Oh, correlation. So, the last thing I'm just going to explain in this slide before we move on is scatter plot. And what a scatter plot just does is almost like a bar graph. The only thing here is that, the values are represented by dots. Now, somebody would ask, why would we keep on going and why would we be doing dots when we can do our graphs? One thing about scatter plots is that scatter plots, by mere visual assessment of your scatter plot, it can tell you something about whether the two values whether the two variables you are thinking about have some kind of relationship or not. So when you look at the scatter plot to the left here now, for instance, you see some kind of clustering. And we don't have enough time to. The ideal thing there would have been to show you several examples so that you can intuitively get a sense of what I'm talking about when I talk about some kind of clustering here. But when you look at the graph on the scatter plot on the right, you don't see that kind of clustering. You just see that everything is scattered all around. All the dots are scattered all around the graph. So by mere visual assessment of a scatter plot, you can get a sense. You can get a sense of whether the variables on the axis here are related. Not just that, you can also get a sense of if they are related, is it a direct kind of correlation, or is it an inverse correlation? And how really tight is the correlation? How much correlated are they? But the point I want you to take away from this is just that a scatter plot is a valid way of graphically displaying your data, and it has the advantage of being, just by visual assessment, being able to make some sense of whether the variables of interest are correlated or not. So we'll be talking about the kind of graphs that we should use. You've noticed that I've not mentioned the pie chart a lot. So even though people use a lot of pie chart, the problem with the pie chart, there are occasions when the pie chart might convey useful information. But the problem with the pie chart is that far too often, there's hardly a time when a pie chart can be useful that another graph would not have been equally useful. A pie chart would almost always have been equally useful. But the problem is when you have more than 3 variables, a pie chart start really losing meaning.
More than 3 categories, you mean?
Oh, sorry. When you have more than 3 categories, a pie chart starts losing meaning, because then, the benefit of a pie chart is being able to look at your pie chart and be able to make meaning of the relative angles that each of the segments have. Now, when you start having more than three categories, you start losing that meaning. Now, for the category 50 to 54, what does that exactly mean? What does this sector actually mean here? The second thing is that if you're not writing in, how many degrees each of those sectors represent, you would need to rely on color coding for people to see the difference in the sectors, in the segments in your pie chart. Not everybody is able to make, not everybody is able to differentiate a whole number of, now here we go. So, and these are the kind of typical pie charts that you find in things like annual reports of some corporate organizations. Now, the thing is, if you just look at this, there's no way this pie chart just at a glance conveys any real information. They're just